Welcome back everyone to this video on Fibonacci numbers. We're going to begin with looking at a definition of what the Fibonacci number sequence are. And the Fibonacci numbers are defined recursively by the first two Fibonacci numbers are both 1, and then every number after that is a sum of the two previous numbers. So the first several Fibonacci numbers are 1, 1, 1 plus 1 is 2, 1 plus 2 is 3, 5, 8, 13, 21, 34, and so forth. So the Fibonacci numbers show up in many unexpected situations and have many beautiful properties. And we begin by presenting a motivating example. So consider a board of length n. How many ways are there to tile this board with squares that have length 1 and dominoes that have length 2? Well, we can let the number of tilings of an n board be little f of n, and we can calculate little f of 4. And we do this manually by just counting all the different possibilities. So we can see that we can have a tiling which is all squares, we can have a tiling which is 2 squares and a domino, a square, domino, square, domino and then 2 squares, or 2 dominoes. So in total, there's 5 possible tilings. But for larger values of n, we obviously can't do this manually, so we're going to need a different strategy. And to do that, we can break this into two cases. We can observe that if an n board begins with a square, then we have to tile an n-1 board. However, if the n board begins with a domino, then we have to tile an n-2 board. Therefore, the number of tilings of an n board is just the number of tilings of an n-1 board plus the number of tilings of an n-2 board. And we can also compute that little f of 1 is equal to 1, and little f of 2 is going to be two cases because it can either be 2 squares or 1 domino. Therefore, we can compute the next several values as little f of 3 is 3, little f of 4 is 5, which is what we found before, little f of 5 is equal to 8. Which should look very familiar to what we just saw with the Fibonacci sequence. And in fact, this is exactly the Fibonacci numbers, except the Fibonacci numbers start with an extra 1 at the beginning. Therefore, little f of n is just going to be the n plus first Fibonacci number. So, using this n tiling method, we can now prove several identities regarding Fibonacci numbers. The first one we're going to take a look at is going to be the sum of the first n Fibonacci numbers, which I claim is the n plus 2th Fibonacci number minus 1. To prove this, we consider the number of tilings of a board of size n plus 1. And we want to consider all of them that include at least one domino in it. So of these, little f of n plus 1 minus 1 use at least one domino, because we have to subtract 1 for the case in which they're all squares. We can now consider the position of the final domino, which is the location k between 1 and n, such that there is a domino covering cells k and k plus 1, and there's all squares beyond that. So up until this point, we can have any combination of squares and dominoes. At cell k, we're going to have a domino, and then after cell k, it's going to be all squares, basically, to the end. So all we have to do is tile the first k minus 1 squares, which can be done in little f of k minus 1 ways. So therefore, we've counted the same thing in two different ways, so we know that the two expressions must be the same. So therefore, little f of n plus 1 minus 1, which is just the n plus 2th Fibonacci number minus 1, is equal to the sum of all these terms of the form little f of k minus 1. But little f of k minus 1 is just going to be the kth Fibonacci number. So the sum of the first n Fibonacci numbers is just f of n plus 2 minus 1. We can now see another fascinating identity that comes out of Pascal's triangle, which is its relation to the Fibonacci number sequence. So if we take a look at the sum of the diagonals of Pascal's triangle, we're always going to get a Fibonacci number. So if we take a look at this first diagonal, that has the sum of 1. Then 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 plus 1 is 5. 1 plus 4 plus 3 is 8, and so forth. And I want to prove that the sum of the diagonal sum of Pascal's triangle is always going to be a Fibonacci number. And let's prove that, and let's make this a mathematically rigorous statement as well. So we want to claim that the n plus first Fibonacci number is just going to be equal to the diagonal sum of Pascal's triangle, which looks like n choose 0, plus n minus 1 choose 1, plus n minus 2 choose 2, and so forth. And that's going to be all terms of the form n minus k choose k, because that's going to be the diagonal. Now to prove that, The left-hand side is just the number of tilings of an n board, as we saw before. If there are k dominoes in a tiling, then there are going to be n minus 2k squares, because remember that a domino takes up 2 positions. So there's going to be 2k plus n minus 2k, or n total squares. So that's going to be a total of k dominoes, n minus 2k squares, for a total of n minus k tiles total. So the number of ways to select k of those tiles and to order them is going to be, because we want to select those to be dominoes, is just going to be n minus k choose k. So therefore, there are little f of n, which is going to be equal to the n plus first Fibonacci number, which is equal to the sum of all these terms of the form n minus k choose k, which is going to exactly prove the identity that we wanted to prove. We're going to take a look at one more interesting Fibonacci identity, and this has to do with the number of tilings of a board of size m plus n. So if we want to show that little f of m plus n is equal to little f of m times little f of n plus little f of m minus 1 times little f of n minus 1. As I said before, the left-hand side is simply the number of tilings of an m plus n board. And now we're in a condition on what happens at a specific position, whether or not there is a domino. So for the right-hand side, we have two cases. If there is no domino at square m, then we're going to be able to break it up quite nicely in that we can break it up all the way up to square m, and then from m plus 1 to m plus n. So there's no breakage basically there. So we can break it up into little f of m times little f of n tilings. However, on the other hand, if there is a domino at square m, well then we have to tile all the squares from 1 to m minus 1, and then m and m plus 1 has a domino there, and then from m plus 2 all the way up to m plus n. So we then have little f of m minus 1 times little f of n minus 1 tilings in this case. So we see that if we add both of these cases together, we get little f of m plus n equals little f of m times little f of n plus f of m minus 1 times f of n minus 1, which adds up the two cases from before. And we can then substitute these values, m equals a and n equals b minus 1, and this gives us this really interesting Fibonacci identity. I'll let you work out how the relation between these two identities works on your own, but this is going to be an important Fibonacci identity that we're going to see later on in the course when we look at the greatest common divisor of two Fibonacci numbers. So keep it in mind. And now we're going to take a brief dive into Binet's formula, which is an exact formula for computing the nth Fibonacci number. So to begin with, I'm going to do a brief interlude on the golden ratio, because that's going to show up in the formula. So two quantities are considered to be in the golden ratio if the ratio of these two quantities is the same as the ratio of their sum to the larger of the two quantities. So in this case, we see that a plus b divided by a is equal to a divided by b, which we define as equal to the golden ratio. So if we let the golden ratio equal to a divided by b in the equation above, we can actually compute the golden ratio, because we see that we get 1 plus 1 divided by the golden ratio equals the golden ratio, which implies the golden ratio squared minus the golden ratio minus 1 equals 0. And using the quadratic formula, we then get that the golden ratio is 1 plus root 5 divided by 2. But you might notice that the quadratic formula actually gives two roots of this equation, and the other root we define as 1 minus root 5 divided by 2 in this case. And both of these roots are going to show up in the very beautiful Binet's formula. So Binet's formula says that the nth Fibonacci number is given by f of n equals the golden ratio to the nth power minus the other root to the nth power divided by the square root of 5. And we can do some basic computation and compute that f of 1 equals 1 and f of 2 equals 1 as well. And we can just do these calculations manually by hand, which I'll leave as an exercise to the viewer. We then assume the result holds for n equals k minus 2 and n equals k minus 1, using the principle of strong induction. And we then show the result holds for n equals k. So we can observe that the golden ratio and the other root are both roots of the quadratic x squared minus x minus 1 equals 0. If we multiply this quadratic by x to the k minus 2th power, We can then see that the golden ratio to the kth power is equal to the golden ratio to the k minus first power plus the golden ratio to the k minus second power, and the same holds for the other root as well. Now, from the definition of Fibonacci numbers, we know that the kth Fibonacci number is equal to the k minus first Fibonacci number plus the k minus second Fibonacci number. And now, using the induction hypothesis, which says that the result holds for n equals k minus 2 and n equals k minus 1, we substitute Binet's formula for k minus 1 here and k minus 2 here. But because they both have a denominator of root 5, we see that we then have the golden ratio to the k minus first power plus the golden ratio to the k minus second power, which is the golden ratio to the kth power. And the same holds, except there's a negative sign for the other root. So we therefore get the golden ratio to the kth power minus the other root to the kth power divided by the square root of 5, which is exactly the desired formula for k, hence Binet's formula is proven. And going back to this golden ratio concept, we can actually see that if we tile a bunch of squares of size Fibonacci number by Fibonacci number, we get something called the golden ratio spiral, which is a really beautiful property in mathematics. If you continue extending this out with a 34 by 34 square and so forth, this spiral is going to continue, and this shows up in a lot of interesting places in both mathematics and nature. Thanks for tuning in, and I look forward to seeing you for the next video.